In our paper, we address the topic energy optimal planning of waypoint-based UAV missions, answering whether minimum distance means minimum energy. I'm Ayush, and my co-authors and I are with the MA department at UC Davis. In this presentation, we'll focus on improving the energy efficiency and sustainability of multi-rotor UAV missions. The overarching goal is to extend the range of UAV by optimizing both mission planning and flight control. We define a mission as a set of n waypoints in 3D space, such that the UAV must visit starting and ending at the origin as seen in the figure. The challenge is to determine the best order of visiting these waypoints that minimize the energy consumption. The key question we aim to answer here is, does the minimum energy order of visiting the waypoints differ from the minimum distance order, which is currently used by solving the traveling salesman problem? To explore this, we model the total energy consumption over the entire mission. To achieve these results, we developed an integrated model that optimizes vehicle trajectories by taking into account all the dynamics of major subsystems, which include the propeller aerodynamics, the ESC motor electromechanical dynamics, the battery electrical dynamics, and the overall rigid body kinetics. To solve this problem, we formulated it as a MILP problem where the objective function we minimize is the total energy consumed over the entire mission. We verified the MILP solution through the enumeration approach to ensure its accuracy. To make the optimization computationally feasible, we generated a table that interpolates the energy cost between different waypoints across a range of X and Z displacements. The table helps us efficiently compute the energy costs for the various segments of the mission as visualized in the 3D plot on the right. We use this approach to generate results for large sets of randomized missions with varying parameters. We find that in 83 to 96% of cases, the minimum distance order and the minimum energy orders do not agree. The difference of energy cost is between 1.6 and 3.4% on average, which can be as big as 14.9%. Specifically selected, sample missions are used to analyze these results in more detail. For example, in this sample 8-waypoint mission, the minimum energy order uses 35.3 kilojoules, whereas the minimum distance trajectory uses 40.6 kilojoules, which is a difference of 15.2%, while minimum energy travels 5% more distance. We identified behaviors which contributed to the difference, and the key takeaways are to reduce the number of vertical flights and combining them with horizontal flights as well. For example, combining 50-meter forward flight and 30-meter up uses only 12% more energy for 90% more distance due to the aerodynamic effects on inflow. Another sample mission is used for experimental validation, which contains 3 waypoints. The minimum energy order here uses 8% less energy, but the minimum energy order combines vertical and horizontal motion more efficiently using 12.4% less energy, covering 42% more distance, which is counterintuitive due to the aerodynamic effects. Thank you very much for your time, and I look forward to answering any questions.